Most people solve this problem in big O of n log n time. But with one small observation, we can actually do it in big O of n time. Welcome back to DKodeTree. Today we are solving LeetCode 1122 relative sort array. We have two arrays as input and our task is to sort the elements of the first array based on the order in which they appear in the second array. In other words, the second array defines the sorting order. And there are a few important rules to keep in mind. All elements in the second array are distinct and every element here in the second array is guaranteed to be present in the first array as well. Like we can see that all these four elements 3, 5, 1 and 7 are distinct and are also present in the first array. Like we have 3 here, 5 at two places, 1 here and 7 here. But there is a catch. Array 1 might contain some extra elements that don't exist in array 2 at all. Like we have 2, 6, 8 and this 6 as well. So we can clearly see that array 1 can have multiple occurrences of the same element and it can have some extra elements as well. So this is our result array and our goal is to place the common elements first in the exact order they appear in array 2. So the first element is 3 and we have 3 present once. So we'll add it to the result. Then we have 5 and we have 5 2 times in our original array. So we'll add 5 2 times. Then we have 1. 1 is present once. We'll add it to the result. And the last element is 7. And we also have one occurrence of 7 in the array. So we'll go ahead and add 7 to the result. So these 5 elements will take these places first. So after doing this, we'll take the leftover elements which are 2, 6, 8 and 6 and then sort them in ascending order. So these will become 2, 6, 6 and 8 and we'll place them at the end of our result. So 2, 6, 6 and 8 will go here. So this is the result array we want to derive. One of the intuitive approaches to solve this problem is to use a frequency hash map or counter. We count how many times each number appears in array 1, like 2 occurs once, 5 occurs twice and so on for all the elements. And then iterate through array 2 to build our result in its order. While we add each element to the result, the number of times it appears in the first array. Till this step, it takes O of n time. But what about these leftover elements? So the next step will be to sort these extra numbers in ascending order and then append them to the result. Now, if we use any standard inbuilt sorting function or any comparison sort to handle these extra numbers, then we are hit with a time complexity of O of n log n. As in worst case, there can be at most n extra elements. So the question is, can we beat this O of n log n limit? And the answer is hidden in the constraints. If we look closely, the problem constraints mention that every element is between 0 and 1000. This means the number of distinct elements is small and fixed. So instead of using a comparison based sort, we can simply use counting sort, which is a non-comparison sorting technique. And as a rule of thumb, when your data is integer based and its range is relatively small, meaning the difference between max and min values is less than or roughly proportional to the number of elements, then counting sort is usually a simple and reliable way to achieve linear time complexity. Now for the implementation, instead of using a hash map, we can simply use an array, say count, for counting the frequency of elements in array 1. And since the constraints mention a limit of 1000, we could just fix the length of count to 1001. But a more adaptive way is to find the maximum element or max num from array 1, which is 8 in this case, and set the size of count array to max num plus 1. This is a better practice because it ensures we use exactly the memory we need and no more. So here's how it works. The index of the count array represents the number itself, while the value at that index stores how many times that number appeared in array 1. And this gives us direct O of 1 access time for every number in our range along with its count. We start by initializing the count array with all zeros. Then we scan through array 1 and for every element we find, we simply increment the value at its corresponding index in the count array. First element is 2, so we'll increment count of 2 from 0 to 1. Next is 5, so we'll increment count of 5. So this will become 1. The next element is 6, so we'll increment the value at the index 6. So let's complete this quickly. Next we have 1, so we'll increment the value at index 1. So this will become 1. Next we have another 5, so we'll increment the value at index 5, so it will become 2. Then we have 1 7, so we increment the value at index 7. Next we have 3, so we'll increment value at index 3. it becomes 1. Next we have 8, so the value at index 8 will become 1. And the last element we have is another 6, so we'll increment the value at index 6 from 1 to 2. Once we have the frequency counts, then we scan the second array and accordingly fill our result array. So in the second array, the first element we have is 3. So we'll go and check in our count array that what is the count of the element at index 3. So we can see that there is only 1 3 from this count. So we'll add 3 ones to the result. Now after processing an element, we do an extra step. This is the most important part. That is, we decrement its count to 0 in the count array. So this 1 will become 0. And this means we have already processed this value and we will not look at it again. The second element in array 2 is 5. And we can say the count of element 5 is 2. So we'll add 5 2 times in our result array. And then decrement its count to 0. So 2 will get replaced by 0 in the count map. The third element is 1. The count is 1 at index 1. So we'll add 1 only once in our result array and decrement its count to 0. And the last element in array 2 is 7. 7 also occur only once in our count map. So we'll add 7 once to our result and decrement its count to 0 in the count map. Finally, once we finish scanning the second array, we are left only with the extra elements that did not appear in the second array, like 2, 6, 8 and 6. More importantly, at this point, our count array contains non-zero values only for those remaining elements, and all other indices will have a count of 0. So now we do one final scan of the count array and add each number to the result according to its remaining count. And this will automatically be in ascending order as the indices are in ascending order. So we start scanning the count array. We can see that the first element has count 0, so we don't need to add anything. Then at index 1 also the value is 0, we don't need to add anything. At index 2 we see that the count stored is 1, so we will add 2 to our result. The next index is 3 and the value is 0. Next we have 4, it also has 0 count. Next 5, it also has 0. And now we have 6 which has 2 as its count. So we will add 6 2 times to our result. After this we have 7 where the count is 0, we can skip it. Then we finally have 8 which has count 1, so we will add 8 to our result. And this gives us the final result as required. The beauty of this approach is that it runs in just O of n time and works in O of n space. Let's analyze this quickly. Let n denote the number of elements in array 1 and m denote the number of elements in array 2. Obviously m will be less than equal to n, as array 2 is made up of elements from array 1 and all the elements in array 2 are distinct. In first step, counting the occurrence of the first array takes O of n time, and in the second step, traversing the second array takes O of m time. But adding elements to the result can take up to O of n time in worst case. So this step takes O of m plus n time. And in the third step, traversing the count array takes at most O of maximum number, and building the result again takes up to O of n. So the overall time complexity becomes O of n plus m plus max num. And since m is less than equal to n, so it reduces to O of n plus max num. And because max num is bounded by 1000, so it is effectively a constant. So the final time complexity simply becomes O of n. And in terms of space complexity, we only use the count array and the result array. So this gives us O of n plus max num, which again simplifies to just O of n. Now let's code this up. So first of all, we'll declare our result variable, which will be a simple list. Next, we will initialize a variable max num, which will contain the maximum value from array 1. We will use this number to set the size of our count array. So now let's initialize our count array. So it will be a simple list with all zeros, and its size will be max num plus 1. Next, we will scan array 1 to count the frequency of elements in it. So for num in arr1, count of num plus equal to 1. That is, we are incrementing the count of this element in our count array. Next, we will scan array 2 to perform the relative sorting. So for num in arr2, we will extend our result. So res.extend a list containing the number times its count. This extend function comes in handy to append a new list to an existing list. So here we are creating a small list with the current number times its count, and we are appending that new list to our existing result. Now the most important step is decrementing the count of the current number in our count array and making it 0, as we have already processed that number. Next, we will scan through the count array to process the remaining elements. So for num in range max num plus 1, as we are using this number as the index of our count array. So now what we will do is we will extend our result in the same way using this number. Here also we will be creating a small list with the current number times its count and appending that new list to our result. Finally, we will simply return our result array. So let's run this. We can see that this works fine and it's a linear algorithm. You can find the different solutions for this problem, including the code we just wrote on my website DKodeTree.com. And even though this counting sort approach is the most optimal solution here, I would still recommend beginners to try implementing the custom sort based solutions at least once. These techniques often come in handy as pre-processing steps in many other problems, so do try them out yourself. And if you found this video helpful, do hit the like button and subscribe to DKodeTree for more such videos. Till then, keep practicing and I will see you in the next one.